In the last video, we introduced the idea of horizontal asymptotes. In this video, we want to develop a method to quickly find horizontal asymptotes for rational functions. So let's recall that a horizontal asymptote describes the long-run behavior of a function. What is the function doing for large positive or negative x? And keeping that in mind, let's look at the first example. What is this function doing for large values of x? Well, recall that a rational function is one polynomial divided by another polynomial. And we know that for large values of x, a polynomial behaves an awful lot like its leading term. So for large values of x, this function behaves a lot like the leading term of the numerator, which is 7x to the fourth, over the leading term of the denominator, which is 5x to the fourth. So for large values of x, this rational function behaves a lot like this function, and we notice that we have x to the fourth over x to the fourth. Those factors will cancel, and we're just left with the ratio of 7 over 5. So what that tells us is as x gets larger and larger, this function approaches a value of 7/5. So by definition, y equal to 7/5 is a horizontal asymptote. One thing that we notice following this line of thought, whenever the degree of the numerator and the degree of the denominator are equal, the x's to that power are going to cancel in this analysis, and we'll just be left with the ratio of the leading coefficients. And so that is our first general rule. If we're looking at a rational function and the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is just given by the ratio of leading coefficients. So in this example, the degree of the numerator and the denominator are both 3. So the horizontal asymptote is given by the ratio of the leading coefficients, which is 6 over 10. Of course, this is a reducible fraction to 3/5. So that is our first rule for finding horizontal asymptotes. And notice the degree of the numerator and denominator played a large role, and essentially our analysis will hinge on the degrees. So let's look at some more examples. Let's change the situation so that the degrees of the numerator are less than the degree of the denominator. Again, for large values of x, polynomials behave like their leading terms. So this rational function is going to behave a lot like 7x cubed over 5x to the fourth. Now, when we cancel the x factors, the numerator is just going to be 7, but since the degree of the denominator is larger, since the power of x in the denominator is larger, we are going to be left with x to some power in the denominator, in this case an x to the first. So this rational function behaves a lot like this expression for large values of x, and notice as x gets larger and larger, this denominator gets larger, and so this fraction will be going toward 0. So because this fraction goes towards 0 as x gets larger and larger, this function will be heading towards 0 as x gets larger. So by definition, y equal to 0 is a horizontal asymptote. So as in the last example, we have a general rule. If the degree of the numerator is less than the degree of the denominator, then y equal to 0 be the horizontal asymptote. So in this example, again, the degree of the numerator is less than the degree of the denominator. So y equal to 0 is a horizontal asymptote. Okay, so we've looked at situations where the degrees are equal, where the degree of the top is less than the degree of the bottom. So now let's look at the other possibility, where the degree of the numerator is greater than the degree of the denominator. Again, we're thinking about large values of x, so we're thinking about the leading term of the numerator and the denominator. In this case, we get 7x to the 5th over 5x to the 4th. And now, because the power on x in this expression is larger in the numerator, we will be left with x to some power in the numerator. In this case, x to the 1st. So now, as x gets larger and larger in the positive or negative direction, the numerator gets larger, and this expression takes off toward infinity or negative infinity. So this function shoots off towards negative or positive infinity as x gets large. So it is not getting closer to any particular real value. Therefore, by definition, probably shouldn't abbreviate that, there is no horizontal asymptote. Looking at this example, we see that the degree of the numerator is again larger than the degree of the denominator. So we conclude that there is no horizontal asymptote. So those are the three rules for finding horizontal asymptotes. If the degrees are equal, the horizontal asymptote is given by the ratio of leading coefficients. If the degree of the numerator is less than the degree of the denominator, then y equal to 0 is the horizontal asymptote. If the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. When the student gets to calculus, they'll see a more rigorous approach to finding horizontal asymptotes, but this should be good enough for our purposes.